Good morning, everybody. It's really a very special occasion for me to have the opportunity to chat with Barry. And I have to tell you a few stories about Barry before we warm up. So you can, I'm sure Barry is an extraordinarily distinguished scholar. Of course, he would deny all of this. So because of that, I have to say it. And so just very briefly, he's a graduate of Rockefeller, and then he actually had a very, very successful scientific career at the Einstein, where he was the chair of cell biology and investigator of the Howard Hughes Medical Institute. And in a time where it was, I would say, very unfashionable, he chose to work on tuberculosis. And I think even as a basic scientist, his heart was always in places where nobody cares or diseases that nobody works on. And so in that realm of scientific endeavor, he actually made quite fabulous discoveries. For those of you who are young in the audience, Barry actually discovered the first cytokine, but he always told me it's not important only to discover things, but you need to name them correctly. And so he named it leukocyte-derived anti-chemotactic factor or something. Nobody could actually say the word. And then somebody came up with a better word called cytokine. And then actually people for a very long time didn't realize that it was discovered by Barry. And so his accomplishment, you know, he's an elected member of the National Academy of Sciences, Institute of Medicine, American Academy of Arts and Sciences, and American Philosophical Society. That's actually an incredible collection which is enjoyed in our university by very few people. And now he's a university professor, which is the highest honor actually in our university. So that means you can hang around in the university, go into whatever school or department and declare yourself faculty of that department. And if you're not, you don't. So it gives a lot of freedom. So that actually helps intellectuals like Barry to disseminate and fertilize between schools, between disciplines, and so on. And Barry was the dean of the School of Public Health, and I actually will talk about that a little bit. And it actually, my entire career actually was spent in his tenure. So I'm actually surprised that he's still willing to talk with me after dealing 10 years at the heart of our heated development. And that was a very fortunate time. The budgets were excellent, and NIH was actually funding close to 20% rate. And it was a really time to implement a lot of things. Global health became very, very popular and important topic. And at the same time, we had a very interesting leadership in the university, which was very challenging for the deans. So his actually life is full of experiences in many, many domains of academia. And of course, both during his tenure as an administrator and as a scientist, but also now, I think one of the really important reasons bringing us here is his involvement with the world, and especially in the developing world. So I want to express my gratitude for Barry to coming to TASSA meeting twice, actually. So he's been in the Boston meeting also, and then share with us some of his wisdom. Also, if you want to strike a conversation with Barry in the hallways, there are a few keywords that will help you. And I'll give you the best one. A certain French lady will actually get you a lot of time with Barry, who is married to a non-popular president right now in France. So you'll have to figure out who that is. So good morning, Barry. Welcome.
Good morning.
How are you?
Well, thank you.
So before we start, can you tell us a little bit about, you had a terrific career as a scientist, but why did you focus on, for example, tuberculosis? And actually, maybe before that, where did you grow up? Why did you decide to become a scientist?
So I grew up in Philadelphia. Everyone in my family was a physician. And two things helped shape my career. One was rebelling against my family, which made it absolutely clear I did not want to follow in their footsteps. And a second was an extraordinary opportunity. Before Sputnik, there was a very small group of people in government that believed the United States had to invest in science for the future because of the Cold War. And one of the things that they started was a program for high school students at the Jackson Memorial Lab in Bar Harbor, the most famous laboratory in the world for doing genetics of mice and preparing mice for research all over the world. And I sent in an application, and I was chosen to go. Spent a wonderful summer in Maine with students from, high school students from all over the country, actually doing what Bruce Alberts talked about, doing surgery on mice, transplants. I got excited about transplant immunology as a high school student. And from that point on, I was involved as an advanced student at other high school programs, even when I was in college. That is a time when people are really plastic and looking for what they want to be when they grow up. And it was a terrific opportunity. And I knew from the minute I finished that summer that I wanted to go into biomedical research without question. I went to Rockefeller I went to college in Massachusetts at a small, not very technical, but liberal arts college, and read lots of books and things outside of science. Then I went to Rockefeller to get a PhD, and the prime reason for going to Rockefeller was there were no classes and no examinations except a final exam. So that science was taught there in a sense the best way we teach science, which is an apprenticeship with someone who does science. And I picked a good laboratory, and I think by trial and error and lots of failures, I learned a bit about how to be independent in science as opposed to a cog in a machine.
So why tuberculosis? So now you finished Rockefeller, you're building your own group. Where did tuberculosis come to your mind?
It didn't. I was one of those people, I remember at the time of the Cuban Missile Crisis, my future wife was very concerned that the world was going to come to an end. And I couldn't understand why people were worried about such trivial matters as the destruction of the planet, because the only thing that counted was science and my experiments and my colleagues' experiments. So I was the least applied scientist that I could have imagined. Until I went and got my first job and discovered this thing called cytokines, where white cells, lymphocytes, have the ability, I like to teach them as bureaucratic cells. They don't do much, but they tell other cells what to do. And they do that very well. And the mechanism by which they do that is producing this non-antibody set of molecules, of which there are many now. And I was quite happy with that. We had a paper in Science, which was a good journal, and my credit was pretty good. And I got an invitation from the World Health Organization, which astonished me, to go to India because the people who headed immunology at WHO believed this was the breakthrough for the most backward disease of all infectious diseases, which was leprosy. And so I packed up and I went to India, and it was an experience I never recovered from. What I learned was two things. One is that science has an enormous amount to provide for the poorest people on the planet. And there are many, many problems that we just don't even bother to study because they're not fashionable in the rich countries. Intellectually, incredibly interesting. I'll just give you the example of leprosy. It's the first bacterial pathogen of man discovered in 1873 by a Norwegian named G. Armauer Hansen that I bet nobody in this room has ever heard of. We know about Robert Koch, which was 9 years later discovered the tubercle bacillus. And the reason is Robert Koch could grow the tubercle bacillus, and no one has yet been able to grow the leprosy bacillus in culture. So it remains as mysterious now as it did then. And I came back and was keen to use my skills in immunology to develop a model for nerve damage in leprosy, which I did. And that got me to think about a whole set of diseases that I would never, ever have thought about in the normal course of life. And the family of bacilli that cause leprosy is the same as the family that causes TB. So the study of one is really a way into the other. And then finally with TB, with the epidemic of AIDS and homeless in the 1980s in New York City where I worked, tuberculosis became an enormous problem. And I had no background or experience, but the Commissioner of Health, who's now, Peggy Hamburg, who's now head of the FDA, reached out to anybody who knew anything about tuberculosis. It was like the Cultural Revolution in China. A generation of people disappeared in science because people thought TB was cured. We had pills for that. It went away. It didn't get away. And it's now roaring back as multi-drug resistant and extremely drug resistant TB. So we are facing another huge problem in TB. Much of this, as you can see, was by sheer chance, not my rational choice.
Yeah, actually, that's the point. I think it's an important point. So there is no such thing as, you know, interesting problem or uninteresting problem. It's just the problem itself is interesting, and sooner or later, something that is a problem in a remote part of the world can actually come to your neighborhood. So you now, from your little lab in Einstein, you one day decided to become a dean. So take it to the next level. So can you tell us shortly why actually did you get tired of science, or was that circuit too narrow for you? Why did you decide to especially become a dean in a school of public health, spend all your life in cell biology?
Adventure. You know, when you get to be 60 and you've done a certain amount that you think you've done as well as you know how to do, you can keep doing the same thing over and over again, or because you know, at least I know, science is the business of young people. We know too much when we get old and when we teach, and that's inhibiting doing really bold, adventurous, risky, dumb things. So this was an adventure. A phone call came from the president of Harvard and asked if I would come up and look at a job. I'd never been to a school of public health. I had worked, I would like to believe, contributing to public health globally for a long time. And there were two requests. If I were to come to Harvard, the hope would be I would have been the first laboratory dean of the School of Public Health in its history, to bring more science, more basic science, to the field of public health. And the second was the hope that Harvard that I would bring a bigger international perspective at Harvard. When I came to the school, only 20% of our students were born abroad. When I left, a third of the student body of the school was international. And I think both of those were reasons that without any appropriate background in public health, I was brought to be dean, and it's been a great adventure, and I've enjoyed it immensely.
So did that come handy to have a background in biomedical sciences to run a public health operation, or do you consider yourself successful in incorporating life sciences into the scene of global health?
Well, one of the wonderful aspects of public health is that nobody really knows what it is. Everybody knows who their doctor is. Everybody knows what the medical system is. Gallup polled the United States public to find out, would you spend $1 a week for biomedical research, even if you don't understand what those people in white coats do? And 77% of the people said they would, because they understand good things come from basic science. When asked, do you know what public health is? 7% said yes. So it's a wonderful field in the sense that it is to be recreated every day. And it can only be done in the most interdisciplinary way. And I would say in many respects we have the most interdisciplinary faculty at Harvard, other than at the college. We have laboratory scientists doing basic discovery and scientific work. We have quantitative people, epidemiologists and biostatisticians. And a third of our faculty are policy people, economists, social scientists. And they all work in the same place, and they all talk to each other, and they understand that the problems of the poor and disadvantaged of this world are not going to be solved by any single discipline. And so one doesn't have to cajole them to work together. They find that a scintillating environment. In fact, there was a young biochemist, molecular biologist named Gokhan, who in my second year as dean, when we had a conversation, I was trying to figure out what he was working on, said that he could do his work anywhere. He was a molecular biologist doing fundamental questions, and in fact, there was no great advantage to being in a school of public health. 5 or 6 years later, when I asked this same not-so-young molecular biologist whether he would be a chairman, which we both know was not good for his career, but we needed him, his response was, you know, I'm glad I stayed because I wouldn't want to be anywhere else because of the interdisciplinary nature and the complexity of the problems and their widespread application. So I'm glad you stayed.
Yeah. So Barry, I want to shift the gear a little bit. Speaking of the world and the changing resource and power structures, actually really influencing the landscape of science, life sciences, applications, policies. And so it is discussed here already that now the developing world is making tremendous investments into education and science, allocation of major resources now that were once unthinkable into infrastructure, capacity building. I mean, you have worked with similar countries with similar dynamics to, for example, what's happening in Turkey. Of course, Turkey is going through this process now, and it is, I think, struggling in finding a good strategy to build a strong foundation, develop a science policy, and then there are, of course, many issues to deal with, ranging from, university structures, intellectual freedom, academic freedom, structuring of the relationship between government and universities. So I want to start by asking you, is this a good thing to do? I mean, why does everybody need to strengthen their science? Why is it important for a blossoming country to develop science? Why does everybody need to invest in science? Just to put the null hypotheses first.
So, one of the reasons that people go into science, or at least I found I went into science, and is every day science changes, and every day the world changes. And one of the challenges is how do you keep changing in an organized and systematic way? How do you learn something new every day? Because in our business, the person who gets there first wins 100% of the marbles. And the person who gets there second gets 0% of the marbles. And so one of the things about science, in a sense, is that it's a self-correcting, continuously learning field. And for countries that are trying to develop, and that is true of every country, from the United States to Burkina Faso, that means that they have to be able to plan for, handle, and make change happen to improve the quality of lives of their people. And if you look just back at recent history, the turning point in China's modernization came, extraordinarily enough, as a recent biography by Ezra Vogel of Deng Xiaoping points out, that in contrast to the party hacks in the past who were down on education, educated people, losing touch with the population, Deng Xiaoping brought in science and technology for the first time in modern China, and that has had an absolutely transformative impact. The same in India, for different reasons. When Nehru was president of India, and when I first went to India, I couldn't eat for 3 days. There were so many kids just in Delhi, let alone in the countryside, with swollen bellies and hair turning brown, copper color from severe malnutrition. You will see none of that there now. But Nehru invested at a time when kids were starving in 11 Indian institutes for technology. It would have been inconceivable that anybody with that kind of leadership would take money that could have gone to starving kids perhaps, but invested in institutes for technology, science and technology. Now India writes a third of all the software in the world, and there are no kids walking around, or very few, with swollen bellies. So that for just purposes of improving economic development and quality of life for people, there is no other way that I'm aware of we have to do it, but then to create new tools. New ideas produce new knowledge, produce new tools. And good governments understand that.
Barry, can I push you a little bit on that topic? That I think it's great to, for example, build a scientific enterprise with hoping that it will actually have good returns. And this is actually a discussion we had here. I mean, Turkey recently, created a ministry called Science, Technology, and Industry, and we're fortunate to have the deputy minister with us right here in front of us. And so I want to ask you, of course, even the name Science, Technology, Industry implies that the mission here is to take science, turn it into technology, turn it into industry. So having a prime incentive as economic return, is there a risk there that it could undermine science? And so there are some examples we know, for example, like Singapore, which attempted this. So can you tell us what is your view of that, thinking about the return, especially the economic return of science, in a place where there is not an established science tradition, educational tradition? How could this model be successful? Or what are the risks or soft points in this?
It's a wonderful question, and any one person's views are not going to answer the question. So let me start with one of my favorite quotes, which I put up on my class listing in the undergraduate science course I now teach at Harvard, which is from Robert Oppenheimer, one of the people who made the atom bomb happen, and said that it's a profound and necessary truth that the great discoveries in science are not made because they're useful. They're made because it was possible to find them. And the possible to find them is why we do science. And that implies a lot of things. One never knows for sure what area of science is going to have practical usefulness. And I think it would be a grave mistake, and has been in some places, to have totally targeted and directed research. There was a massive effort in this country of getting a bunch of experts around the table for a national cancer plan. And the answer was we didn't know enough about cancer to be able to have a national war on cancer. Wars on things one has to be very cautious of. We still haven't eradicated polio. Polio was supposed to be eradicated by the year 2000. There was lots we didn't know, including technically at the scientific level, that we didn't know. So I think one has to be cautious about promising to deliver. I think we have also to appreciate that there has to be a number of things that to ordinary people would seem very peculiar. We have to encourage failure. I've been privileged to have, even during my deanship, a grant from the Gates Foundation on vaccines against TB. And it's called the Grand Challenges, and we were invited to come to meetings. And in the first of the meetings, Bill Gates said that his expectation was that of the monies he's putting into research in health, if more than 1 in 20 grants paid off with something useful, he wasn't taking enough risk. And I think one has to hold that in mind. If it's sure bets, then we're losing the battle of knowledge and science. And one of the problems with the NIH, to be absolutely honest, scientists are very conservative, believe it or not. Intellectually, they may be progressive, but when it comes to giving away the public's money, study sections at NIH are notoriously conservative. You basically have to have the data to show the experiment is going to work before you can get the money to do the experiment that you've already done. Maybe that's good, maybe that protects the public's money, but as you know, the NIH has been looking for mechanisms that are out of the box, that don't have 20 obvious people sitting around, incentives grant, pioneer grants, to get out of the bind that scientists are protecting the public's money because they want short-term gains, just like the people in Congress want short-term gains. So I think that one has to create mechanisms that allow failure and allow what we would call in physics degeneracy. There's no one lab that knows enough that you could guarantee they will produce the product that you think would be helpful, a vaccine, a drug for cancer. So one needs lots of labs doing the same sorts of things. It never happens that they stay doing the same things. But what one then funds is diversity in the same way you would diversify a financial portfolio, because you never know which scientist working on the same cancer is going to find an insight that someone else will not. And a second area of degeneracy, and more than one person doing the same thing. When SARS hit, it was shocking to me that we had 2 laboratories in the United States of all the 6,000 biomedical scientists working on coronaviruses. Had we not had those 2 laboratories, I'm not sure we would still know what the cause of SARS was. So that there has to be a sense of diversity. And in the context of India or China or Turkey, perhaps, you don't have to do everything in Turkey to be part of the scientific community. So I like to say that all health is local, all health policy is national, and all health research is global. I would cite an example from the EU, which in my field was really terrible. Each country had a small number of labs working on immunology and vaccines. Because of the EU and the pressure to get large amounts of money that required collaboration between scientists in 3 countries, and even projects working with developing countries in Africa, where there had to be 2 or 3 European countries and countries in developing world. It is astonishing that in 5 years, some of the most advanced science and development is being done in countries like Spain that never published scientific papers at the whole time that I was a student. So the consequences are, in a global community, the question is not what is Turkey's contribution to science alone. It's how can Turkey leverage the knowledge that's out there for its benefit and the benefit of people elsewhere.
So can I ask you that in follow-up of that, what do you think are the pillars of that? For example, is it the recruitment of the young faculty? So how is that young faculty could be, for example, empowered? And we have had discussions off the line with you. For example, what's the life of a junior faculty? So if for example, a postdoc goes to one of our powerful universities here, how would the life of such a young faculty could be empowered to tap into, his or her own curiosity? And in your tenure as a dean, you recruited a lot of faculty. So what was some of the tension points in the life of a young faculty?
I think you've said what is absolutely crucial, and that is one is looking in faculty not for what they did yesterday or what they're going to do for tomorrow, but a trajectory of how broad their range of curiosity is.
Why is it so important?
Because that's where the risks are. That's where the new findings are. You know, Pasteur said, chance favors the prepared mind. An awful lot of what happens in a laboratory and research is not planned, is not intellectually conceived of. It happens. And when it happens, how does one identify people who can take advantage of opportunities? So the way that one has to do that, and I have some very strong feelings, and that is junior faculty, if you think they have a potential long-term trajectory, that they can be independent, not dependent on anybody. The major question that I got from junior faculty when I first came to the School of Public Health, and mercifully not at the end, is it better to work on my boss's grant, my department chairman's grant? That's how I protect my career, by doing something my chair wants to do or for which there's lots of money? And if so, how to identify my unique contribution, which is what determines tenure and recognition? That's a tension that is inevitable. And I think the answer has always been the most important thing is to be able to be in a position where you have the resources to pursue new ideas simultaneously with those to which you're already committed, whether the money is from your boss or whether it's startup money from the dean. Do things that you are passionate about doing. And to do so, the institution has an obligation to help you do that. And one way to help you do that is to give you protected time. And I know with the tremendous increase in students, for example, in Turkey, in India, I know the India case very well. There is almost no clinical research in India because the patient load is so great. There's no time off for doctors to be able to do research. And I think that in order to get scientists started, they have to have free time to be able to just do science. Let me also say that one of the things I respect about Harvard, past the initial early stages, is no faculty members can buy out teaching time. I think we invest in young people to be scientists. We're also investing in them to be teachers and to be role models for students. And so nobody can buy out of teaching at my school, and I'm very pleased with that. And I don't think the loads are crushing that the teaching has impaired anybody's ability to be a good scientist. And the second thing is, in our place, it was the case in, I think, other parts of universities. We've just hired you, you're terrific, Harvard is terrific, go to it, you're on your own. I don't think that's a healthy circumstance. We created a system of mentoring where there are at least 2 mentors for every junior faculty member in their first 6 years, actually. And one is usually from the department who can help them with things hopefully related to what they do. And one is often out of the department that can give them a sense of perspective that what their department thinks is the most important question may not be what everybody else thinks. So I think junior faculty need lots of support, lots of mentoring, and lots of role models.
Yeah, I mean, many of the junior faculty, I think, will appreciate that, especially related to protected time in the early years. So you're all required to teach, but not in the beginning.
Not in the beginning.
Of building your careers. So, Barry, I want to ask you actually one more thing about this curiosity in science. I'm obsessed with this, and I mentioned this in my talk also. So, many of the, actually, I was thinking about this, many of the greatest discoveries that had the most implication for human life did not actually come from people who decided that, okay, I'm going to cure cancer. So can you talk
So
in
my field, it's a wonderful question, and I've really pondered this a lot because the pressure is so great to use science to solve worldly problems. And I think that is a crucial role for science. It's why in the long run, people will pay $1 a week, even they don't understand where that dollar goes. They know somehow good things come out of that. What they don't know is how they come out of it. So I give you my 3 examples in the fields that I know and the people that I know. One of my heroes in science was an extraordinary geneticist, later president of the Rockefeller University, named Joshua Lederberg. Maybe some people here knew Lederberg. Lederberg was interested in genetics and evolution. And the question that was on his mind was, how do you get from E. coli to an elephant? And do you do it by one mutation in one gene at a time? That struck him as exceedingly inefficient. So the question was, are there mechanisms to take up big chunks of genes from one bug to another or from one organism to another? Well, we have a name for that. It's called sex. And so he discovered recombination, where big chunks of genes can speed evolution up tremendously. He was ridiculed in the press as, this guy only cared about sex in bacteria. Sex in bacteria began the genetic revolution. It began biotechnology. It began recombinant DNA. And, Josh was very, very foresighted. But whether he said he had no idea how fruitful and practically important pursuing sex in bacteria actually turned out to be. I note that nobody laughs at sex in bacteria anymore. It's become too important. So that was a person, brilliant person, pursuing a fundamentally important question using an extraordinary curiosity. The second is perhaps the most practical thing in my field, which is monoclonal antibodies. All the stuff that you saw yesterday where cells were being marked to distinguish this cell or that cell or a lymphocyte or a macrophage, that's done by monoclonal antibodies. So how did that come about? So I know this very well. There was a guy named Caesar Milstein at Cambridge University who was interested in production of antibody by B cells. And antibodies are a differentiated function of B cells. When they finish, that's the only thing they know how to do. And when they finally finish making buckets of antibody, they die. That's all they do. Now, there was a business in cancer where people had, particularly a very famous guy who ran the Nobel Institute in the Karolinska Institute in Sweden. If you took a differentiated cell, a heart cell, a muscle cell, a pancreas cell, and made it fuse with a cancer cell, the cancer cell invariably disturbed the production of the differentiated product, and you ended up with a non-productive, non-differentiated, bigger cancer cell. So they tried to do this with cells in the immune system, and they did it. And lo and behold, the B cell production of antibody was not extinguished, in contrast to almost all other fused cells. But in fact, they continued to make antibodies, but they continued to grow, and B cells don't continue to grow. And then one has an infinite capacity now to grow cells producing a single antibody. The most exciting discovery in HIV/AIDS was by David Baltimore in the last year, that you could in fact give genes to cells and enable the B cells to make antibodies almost forever. And if those antibodies protect against infection, against HIV, we have a first new real breakthrough in a long time. And the third example was a bunch of guys studying viruses in California. Currently now, former head of NIH, Harold Varmus, a former college mate of mine, and Michael Bishop, who were interested in studying chickens and puzzled by the fact that they knew a lot about chicken leukosis virus. They couldn't understand why there were a whole lot of chickens out there that had DNA sequences that weren't chicken sequences. They looked very much like virus sequences. And from those studies came the understanding that we have genes in our body, probably picked up from viruses, that are called oncogenes, that actually have the ability that some viruses have in earlier forms to be able to create cancer. They were trying to figure out why there was weird viral DNA in chickens, and they found one of the key fundamental observations. So it's very difficult to say, in the war on cancer, which I mentioned, the only thing that came out of the war on cancer usefully, in my view, was the DNA sequence of a mouse leukemia virus, which was the basis for identifying HIV as a member of that family. It didn't solve the cancer problem, but these guys pursuing their curiosities made far more important contributions.
So let me follow up with maybe another policy-related question. So this, let's say, here's the government sitting here, putting a lot of money or planning to put a lot of money. And naturally, they're interested in what would be the return. So the reflex would be, you know, I am putting the money, so I should have a piece in this pie. So why should a government accept to be on the sidelines, for example, of research or academic decisions? Is it wise? Or what is the productive way to incorporate into this decision making?
It's a hard question to answer because it's a complicated relationship. And the excesses on either side are completely obvious. I like to think of the example of the NIH. The NIH set up a unique mechanism, very different still than most other government agencies. So in the Office of Naval Research, when you needed research on radar or you need research on something, there's a project officer. And that project officer has a budget, and he decides what he will fund. And really no one questions that, at least for some period of time. And if the project doesn't work, the project officer gets fired. That's the incentive in the system. It's a pretty powerful incentive. And that's how science was done. And that's how radar was invented. And a lot of technology was invented. And in some senses, it's the most efficient way to do things if you know exactly what you want and how to get there. At the NIH, they made a very Darwinian decision. And I've talked with Letterberg about the genetic basis for this kind of decision. If you had a bunch of senators or government officials sitting in a room in 1952, listening where the problem was, what are we going to do about polio? And two guys come in and make their case. And one guy from the Harvard School of Public Health says, I can keep these people alive. I've invented the iron lung. We have the tool. We only have to get it out there. And the other guy was a guy with red eyes and a white coat that says, I don't have anything at the moment, but give me some money and I'll make you a vaccine against polio. I would ask you to guess what the government officials would do in that circumstance. So the Darwinian selection was as best exemplified. There was a foundation, the Ellison Foundation, that Letterberg was chair of, and I and 6 other people, including 2 other Nobel laureates, were members of. And we wanted to move from what they were funding to really innovative ideas in the origins of psychiatric illness. And the question was, we were sitting around the table deciding like what they should, what the hot areas to get into the basic fundamental biology of psychiatric disease. And Josh just stopped us and said, you know, why should we think we have the totality of ideas? Why don't we put the money on the table and select for the best ideas that come in? And that's the Darwinian idea of science. If you put up challenges, whether it's Bill Gates and the grand challenges, there are people with ideas that we don't know about. There are people we do know about in one area, which we found to be very useful in this foundation, moving into areas they'd never worked in before. And at NIH, if you haven't worked in it before, you have a very low chance of getting funded. So selecting for the ideas is what you want to do in science, not selecting for the project that you want to fund.
Great. So, Barry, we're actually coming to end of our time. So now I'm going to ask you my hot potato questions. So one is actually, you're making an incredibly compelling story where, you know, the science and discovery, where is the creativity actually, and how to promote that. And there has been tremendous amount of actually scientific development accomplished in this century especially. But why do people still have difficulty in believing in science? And I want to ask you actually 3 examples, for example. One of them was mentioned by Bruce Alberts. So there is climate change, and the impact is very clear. The evidence is mounting and very, very strong. But why does the scientific truth cannot determine the agenda? So is there something inherently deficient in scientific truth to determine the clear and undiscussable path for the governments, for the policymakers? The second is, for example, again, I think it was in Bruce's talk, genetically modified crops. The evidence is very clear, yet one newspaper report or a declaration from one senator or one minister can actually undo a century of research. And the third one is evolution, for example. The evidence is very clear and solid, whereas in America, for example, there are places which teach kids that life started 6,000 years ago. In my laboratory, I have evidence that it started at least 2 billion years ago. And the one that we cannot experimentally prove could be even further. So why do you think, despite so much scientific advance, it is difficult to make people believe in evidence?
Wow. When I became dean, the School of Public Health had a mission statement, which was to improve the public's health by learning and discovery. Learning being the broadest sense, education, discovery being curiosity-driven inquiry that you heard beautifully from Bruce. I changed that with the support of the faculty and the opposition, by the way, of the university, to add to that communication. Because to have all the knowledge in the world sitting in the School of Public Health, if it doesn't change the health of anybody in the outside world, is essentially useless. And of all the things that we do many things in science inefficiently and perhaps not with the best ideas. The one we do least well is communicate with the public. And there's 2 parts to that issue. One is the public has to have some understanding of science, because it's very hard to understand what we do in the general sense if there is no science in education. And there are many, many people who go through an education with essentially no understanding of science. I mean, memorizing certain facts of science is not to understand the process of science and what it does. So that's one of the issues. We do a very poor job. And part of the reason we do a poor job is the media is under their own selective pressures. So the line is that when I would call up a journalist and say, God, they've just wiped out the last polio case in India. There hasn't been a polio case in India in a year. The response that is typical is, good news is no news. But give me a scandal, give me a fraud, a scientific fraud. That excites the people. And that's just the way the world is. So I think what that calls into question, and we heard something from the minister yesterday, we have to have the freedom of inquiry. We have to have academic freedom. We have to have people who can say things and not fear that their presidents will fire them, even if they're unpleasant and unconventional things. If we believe in evidence, which the scientific community does, if the ideas are crazy, they will soon be crazy. If the fake cures for cancer are not cures for cancer, we have a scientific method to get at that. but we should not suppress people for their thoughts and their beliefs. But we have to preserve the integrity of science, and there needs to be a regulatory framework and a process by which claims of fraud or stealing of ideas is dealt with in a serious way at the academic community, or the integrity of science is threatened by one or two anecdotal cases that's blown up in the media. It seems to me that that's absolutely fundamental to that. And the third thing is something we can't control any longer, and that's the internet. So when H1N1 flu hit Mexico, obviously I'd been through a couple other flu epidemics. I went on to I had to give a talk, and I went on the internet, and I typed in flu, influenza, and I read the first 200 websites. And it was a shocking experience, and I think this is something quite serious. Have not a solution for that. I would say there may have been 5 that had accurate information, and the other 150 were diatribes against vaccines designed to make money for pharma companies and to kill kids at the worst. How the world will deal with the information or misinformation on the internet is a new phenomenon that has easily raised and become viral. Any way to make people skeptical, I think not just of science, but certainly of science. And I think we're going to have to think of thoughtful ways in which the evidence becomes available to people, and not just the hearsay or the word of scientists.
Unfortunately, we came to the end of our time. It's a delight to have this opportunity actually to chat with you. And I will leave it at the chair of the conference, either to allow a discussion with the audience for a few minutes, if you would be kind enough to take some questions. And thank you very much.
Thank you very much for your comments. I think you very rightly mentioned the fact that one of the strengths of the science funding in the United States is that you, for example, agencies fund similar work at different places to make sure that the diversity is benefiting the end result. But I think also another strength that the United States has is that it is decentralized in the government. There are many agencies of the government, not just NSF, not just NIH, but there is Office of Naval Research, Air Force Office of Scientific Research, etc. And these are funding research in a variety of ways. Whereas NSF, for example, may shackle the researcher a lot more, requiring 15-page proposals every 3 years and such. Office of Naval Research will allow you a much longer perspective. So I think for the Turkish government, it is important that the funding is not centralized in the government. It's not centralized out there in the research area, but it shouldn't also be centralized in the government. There should be multiple parts of the government funding work. What would you think about that?
I think you've said that is one of the strengths of our system. And the other point is that it's select for ideas. It not be the only, the government can't be the only place that has ideas.
You usually don't need a mic, but let me use it anyway. I think this has been wonderful, discussion. Well, I'd like to thank you for that, first of all.
Thank you.
And Gokhan, for doing this. But my question is, how do you think our current system of tenure and pressures to publish affect young scientists tackle problems which are potentially more risky?
Very severely. The issue of tenure is, I think, important at a level that I would not have guessed. I've never been a big fan of tenure. I'm a great fan of competition of ideas. And I think there are humane ways, in the absence of tenure, when people cease to be productive, in some reasonable process, they're given a period of time to taper off. Because I think, as I said in the beginning, I strongly believe the new ideas come from new people. But I'll just give you one example of the importance of tenure, which I think one has to take very seriously. In the debates at Harvard University, in the Faculty of Arts and Sciences, as to whether the president should receive a vote of no confidence or not a single untenured faculty member spoke. And that tells you the intimidating power implicit in the authority of department chairs and university presidents and tenures, and the risk to careers of speaking freely. And I feel that we have to encourage junior people to speak freely to help us change and make our universities better.
I enjoyed your answers very much, and the questions as well. So thank you very much. So I had a question about, we mentioned NIH and some of the changes. NIH is going through some changes, as you know, right now. And one of their big emphasis is on translational research. So even in this country, they are trying to push science into a more applied direction, with the outcome of coming up with potential, new drugs, etc. So this kind of research is now being moved away from pharmaceutical industry, and it's kind of thrown into the arms of the scientists. So what are your thoughts about this? Is this a good direction to go?
I have two thoughts. One is the thought of Lord Porter, who was president of the Royal Society, who has a line that I like a lot, and said, basically, there are only two kinds of science: applied science and not yet applied science. And the other is from a former biochemist at Cornell named F. Racker, who came and gave a talk to our students when I was in New York and said, look, this was when grant funding was bad. If grant funding is bad and you can't get funded for basic science, do applied science. You will soon find you're doing basic science.
One last question, Gokhan. You choose it.
Okay.
Does it have to be that far, Gokhan?
It's over there.
Thank you so much. I'm a PhD student, and my question is about, because we just submitted NIH grant with my advisor, and I wrote it basically. And my question is, how reviewers are assigned. For example, when NIH announces a grant, it has a specific mission, and the reviewers might not have the same mission. Like they might be looking at something else at a grant, like how it is well written, or it is innovative, or it has good results. So if the reviewer's mission is not matching with the mission of that specific grant, so we might not get this grant. So how the reviewers are assigned?
But maybe you can actually say a few words about the review process itself. Also the ones that you have seen in India, actually. That's an important one we didn't have a chance to cover.
So the review process is an imperfect process, whether it's the project manager who decides entirely by himself what's important, or you have 20 people sitting around a table at an NIH study section. There is something called human fallibility, and not all new ideas are recognized as good ideas, so that there's intrinsic fallibility in any review process. One of the worries of countries, including Canada, is that everybody knows everybody, and there is difficulty getting absolutely independent reviews in countries that don't have a big scientific community. And what happens then is there's a lot of either nepotism or favoritism. This young person was trained in this guy's lab. He's a good guy. We've worked with him before. We'll fund this one and not that one. So I think that the independence of the review and focusing on the piece of paper in front. I had the awesome task as a reviewer from a grant from a Nobel laureate to turn it down, because I knew he was brilliant and I knew he was going to do what he said he was going to do. But the grant that I was comparing with all the other grants was really lousy, and it didn't get funded. And he wrote a better grant and it got funded next time. So there is a communication process. But the point of the grant is that it requires independent reviewers, even with their fallibility, with the recognition that things are too crazy and too wild, they're not going to get funded. So there is a certain, I think, strategy involved in writing grants in which you can explain to people why they should be funded. And that's a requirement in all grants. And it's also, not every grant is applied, but if you were able to do what you proposed to do, if everything worked, is this worth funding more than some other grant? And I think those are decisions that I think are honestly made. I think in the history of NIH since 1949, there were fewer than 10 cases of either conflict of interest or bias or stealing of ideas from the thousands and thousands of grants that are done. It's an imperfect process. Everybody who has a paper turned down believes the reviewers are idiots. Certainly, I do. But we have bought into the process, because some days we're reviewers as well. And that's why it's a self-refining system.
Thank you so much. This was a true delight.
Thank you.